Hi, and welcome to our third lecture in aerodynamics. Last time, we briefly covered the variables that most commonly appear in the study of aerodynamics and how these fluid characteristics lead to forces on an object. Today, we'll cover how distributions of these flow properties, specifically the pressure and shear, generate body forces on an object and the resulting moment. So, let's jump right in. In aerodynamics, we're generally concerned with the forces produced on a body traveling through air. As we all know by now, an object moving through a fluid feels force, which is like the motto of aerodynamics. So, let's draw our object in a flow, in this case an airfoil. The flow moves around the object, changes direction, and results in a net force on the object. From our fluid mechanics studies, we know that flow can be wildly complicated and difficult to understand. Things can be separated, turbulent, and impossible to calculate. However, one nice simplicity of fluid forcing is that it really can only come from two sources, regardless of how complicated the flow is. There are normal forces on the surface of an object. These are called the pressure forces. Typically, the force is distributed over the surface, which is why we talk about it in terms of a pressure, which is a force per unit area. And the other way to force a surface is through tangential forcing, which we call shear stress. Stress is also a force per unit area. Commonly, this is associated with the viscous force and the flow viscosity, mostly because it is the dominant shear term in the governing equations of fluid mechanics. Often in aerodynamics, the surfaces that the air passes over are complicated, and this makes the pressure and shear distributions over that surface also complicated. Take, for example, the pressure and shear distribution over an airfoil. These two distributions are the contributors to the lift and drag of the foil. The pressure distribution is capital P, and if we are thinking of surface pressure, then we consider it along the curve S, which represents the foil surface. Similarly, the shear stress is the Greek letter tau, also presented along the S curve. Here, I'd like to pause and consider this curve S, because it will pop up in aerodynamics a lot. You may be wondering, why make it a function of S, and not just X and Y, as we would with any other flow field? The coordinate S follows a curve and can only represent a point on that curve. X and Y define the entire two-dimensional space and can define any point on that plane. All of the points on S can be equally represented by X and Y. However, in aerodynamics we encounter a ton of complicated surfaces. Cylinders, spheres, airfoils, fuselages, yada yada. And for the most part, we care about the forces on the object, which happens at the surface where the air meets the object. As we'll see from the math in this video, it is more convenient to define the curve S and use that than to keep track of the X and Y coordinates of the surface. Okay, back to it. Pressure and shear both produce a net force on the object. Let's consider some simple examples of how the distribution results in a net force. Consider inviscid flow over a stationary cylinder. Inviscid here meaning we will primarily be concerned with the pressure distribution and will ignore viscosity. We can mark our X and Y axis as well as the S coordinate, which follows the cylinder surface. This is what the pressure distribution would look like, where it is large on the top and bottom of the cylinder and smaller in the front and back. Notice that the pressure distribution is the same when comparing the top and bottom as well as the front and back. But this means that there is no net force in the X and Y directions on our cylinder. Every pressure has an equal and opposite on the cylinder. No pressure difference means no net force. A quick historical note, this actually caused the famous D'Alembert's paradox. Early in our understanding of fluid mechanics, we didn't know about viscous forces. So everything we knew about fluid forcing came from pressure. D'Alembert noticed that, according to his equations, there should be absolutely no drag on the cylinder, like our case here. Unfortunately, he also noticed that in the real world, of course cylinders had drag. Technically, this was just a flaw in our understanding of the fluid mechanics at the time, but when you're super smart like he was, it gets to be called a paradox. Now that we're familiar with a stationary cylinder, let's consider a rotating one. When a cylinder rotates, the stagnation points move down on the cylinder and more air passes over the top than the bottom. This results in a pressure distribution that looks something like what you see here. There are regions of high pressure magnitudes at the top and lower magnitudes at the bottom. Still, the pressure distribution is the same when comparing the front and back of the cylinder, mirrored across the x-axis. But the pressure distribution is different between the top and the bottom now. This difference causes a net force in the y direction, and that's what we call lift in aerodynamics. But we still do not have a force in the x direction, which is drag, because the pressure forces are equally pushing on the front and back of the cylinder. This is the primary principle that makes curveballs curve in baseball, softball, and in cricket. As the ball spins, it generates a net force in the direction opposite of the spin, and the ball will change its dynamics. However, to this point, our cases have been inviscid. Let's consider a stationary cylinder and a viscous fluid. We can't go into too much detail, and this flow field would probably be complex, but viscosity induces a boundary layer on the surface, which grows, and at the back of the cylinder is separated. This separation dramatically changes the pressure distribution on the surface of the cylinder. Here we see a different pressure distribution when comparing the front and back of the cylinder, but the same pressure distribution comparing the top and the bottom. This means that the pressure distribution leads to a net force in the x direction this time, and this is the drag. In this case, there is no net force in the y direction, or no lift. As you can see, depending on the distribution of the pressure and shear along the surface, we can get different combinations of lift and drag. Now, we have a good handle on simple configurations. Let's see what happens with an airfoil. Take a second and draw out an airfoil at an angle in a flow field. The dashed line here represents the airfoil chord line, which connects the leading edge and trailing edge of the foil, and the length of the chord is C, or the chord length. The angle of the foil relative to the incoming flow is called the angle of attack. Let's define that the x direction is along the chord line and the y direction is perpendicular. Typically, x and y are put at the leading edge, but for now we've just drawn it here for convenience. And we have our S-curve that represents the foil surface. The flow causes a force, here labeled R, which is the total net force from the pressure and shear distributions. This force can be decomposed in two ways. The first is to decompose it into the x and y coordinates relative to the chord line of the foil. The force in y is labeled N, and the force in x is A. Alternatively, you can decompose the r vector into components relative to the flow field itself. Here, the force perpendicular to the flow is L for lift, and parallel flow is D for drag. Drag and lift are always relative to the flow velocity direction and not necessarily the object. Depending on your situation, it can be beneficial to use either of these decompositions, but typically lift and drag are more user-friendly. If you happen to know the forces of N and A relative to the chord line, you can convert them into lift and drag with a simple geometrical expression. Let's assume we have somehow calculated or have been given the pressure and shear distribution along our airfoil surface. Now, we want to be able to calculate the vertical and horizontal forces from these distributions, and to do this we'll need to deploy calculus. Consider an airfoil at an angle of attack alpha. The airfoil has a finite span with length L. Now, we want to divide the foil surface up into infinitesimally small segments. This segment has a width of delta S. And, for convenience, we will consider the upper and lower surface of the foil separately, which will be denoted on variables with a subscript U for upper and L for lower. On this really small segment, we have a pressure normal to the local surface and a shear stress tangential to it. Our force is delta N, because we are considering only the force from the shaded region. Force is a pressure or stress times an area, so we multiply our pressure and our stress on that shaded region by the area of the shaded region. Note here that the pressure and the shear are relative to the local surface, which might be at an angle relative to the chord line. The angle between the local surface and the chord line is theta. We do this for both the y and x directions. Now, these equations have the finite span length L in them, because we need to have three-dimensional bodies to produce forces. However, in aerodynamics we do a lot of considering forces per unit span, meaning we divide through by the span entirely. This takes span out of the equations. It means that our equations apply to foils of any span length, so they become more general. Here, we will denote per unit span quantities as having an apostrophe, or a prime. The new equations, after dividing through by span, become the following. These represent the forces per unit span of the foil perpendicular and parallel to the chord line from the segment alone. But we need to consider the entire surface of the foil and not just that segment. So what we do is we take up all the little segments on the foil surface, calculate the forces for each one of those segments, and add them all up to get the overall body force. In other words, we simply use integration over the foil upper and lower surface along the curve S. To get the total N force, we integrate from the leading edge to the trailing edge of the delta equations from above, but here we have transformed our deltas into differentials, or lowercase d. We do this for both the upper and lower surface separately and add them together. Both the force perpendicular to the chord line, N, and parallel to the chord line, A, get the same treatment. Remember, these apostrophes mean that it is force per unit span. In order to get the actual force on an actual foil, we need to multiply this quantity by the foil's span length. Let's mark these equations as 1 and 2. We might need them later. This covers the body forces, but the pressure and shear distribution also cause a moment on the body, or a twisting action. You might recall that a moment is just a force multiplied by the distance called a moment arm. So, we can treat the foil problem similarly, but instead now consider the moment caused by pressure and shear. Let's draw our foil again with the same parameters labeled and the same shaded segment with width delta S. Here, we can be a bit more careful to put the origin at the leading edge where it should be, and now we are concerned with the moment around that leading edge. This is the twisting that you would feel if you were to try to hold the foil at the leading edge in this flow. First, we consider the moment contribution from only the small segment, and we're going to divide through by the span so that we have moment per unit span. The pressure and shear are transformed into the x and y coordinates through trigonometry based on theta and are multiplied by the width of the segment. This represents the force at that segment. Then, we multiply by x, the distance to the segment from the leading edge in the x direction. This is our moment arm. This happens in both the x and y directions, which are added together. And, as before, we need to add up the effect of all the little segments to get the overall body moment about the leading edge. Let's take a second and do that now. The end result is the total moment per unit span of the upper and lower surfaces added together. So, We now know how we would go from the pressure and stress distributions to get the resulting body forces and moments on an object. Anytime derivations or equations get a little bit heavy, I always naturally ask whether anyone will actually use this stuff. And I think that's a fair question here. In this case, if you're an aerodynamicist, you very well may need to use equations like these. Working in the field, you can get your results through either physical measurement or simulations. Through measurements, maybe you have a scaled down model of your foil in a wind tunnel and you want to calculate the body forces. You could outfit your foil with pressure taps all over the foil surface and get an estimate of the pressure distribution. However, the shear stress is much harder to obtain experimentally, especially the distribution of the shear stress. So, at most, you could find the lift and drag from the pressure alone and hope that shear wasn't all that important. However, in the case of measurements, the lift, drag, and moment are much easier to measure directly. However, simulations solve for the flow field around the object. This is something called CFD, or computational fluid dynamics, and is very popular in industry. This simulation solves for the entire surrounding flow field and can feed you the results as the pressure and shear in X and Y. You can transform these into the S-coordinate to represent the surface stresses. From there, you would absolutely need to solve for the lift, drag, and moment using these equations. Often, these functions are already built into the software. So, the conclusion is, with the popularity of CFD, I think it's fair to say that you might find yourself needing this stuff. Now, you have calculated your two forces N and A with your fancy new equations. But where do they go? As of right now, they are just arbitrary floating forces with no home, but in reality, they're centered about a point on the foil. This point is on the chord line and is at the center of pressure. Let's do a simple non-fluids example first to better understand. Consider a plate covered in snow, like a flat roof or a shovel. The snow produces uniform loading on this plate, an evenly distributed force or pressure, if you will. Now, you have to decide where you want to attach something to this plate at a point to hold it, like the handle of your shovel. If you hold this plate at the left edge, x equals 0, you're going to feel a positive moment due to the snow forcing. This would probably be a poor way to design a shovel. However, if you hold it in the center, the plate will be balanced such that there is no moment at that location. We can see this more quantitatively if we consider the moment as a function of the distance along the plate, and the location of the balance point is where this moment is 0. Although airfoils have much more complicated load distributions, they also have this balance point where there is no moment. This point is called the center of pressure. So, let's sketch a foil and try and eyeball where our forces are centered and assume that the center of pressure is somewhere along the chord. We need to find some way to calculate the XCP from what we know already. Now, what we do know is that there is a moment about the leading edge. We have an equation for it, and that this moment must be due to the force N on the foil. What we need to do is solve for the moment arm that N would need to exist at in order to create the moment M. Knowing that a moment is just a force times distance, this is fairly straightforward. We can solve for XCP by dividing the moment by the normal force. Note here that it's negative because a positive N force produces a negative moment. And if we had lift and not N, as long as the angle of attack is small, you can interchange lift and N without much issue. So that's great. We now know the center of pressure location and where our forces actually go on the foil in our diagrams. We have a more complete understanding. However, I have a bit of a spoiler. In reality, the center of pressure isn't all that useful for people who design airfoils. This is because it moves. If the airfoil changes speed or angle of attack, the XCP can shift dramatically. So, no foil has any single center of pressure, which makes it harder to utilize. What we end up doing to define a foil is to document the lift, drag, and moment about a predefined point on the foil, or the quarter chord of the foil. The quarter chord is always in the same spot by definition, and we just need to know what moment exists there under any condition. So, if you were looking at the performance of a NACA 0012 in a book, you would see 3 charts. First, the lift as a function of angle of attack, then the drag, and then the moment. They would look something like this. Now, you look at these charts, figure out what angle you plan to be at and what flow velocity, and now you know what forces and moment per unit span to expect. These ultimately tell you how much weight you can carry, how much thrust you will need, and where to put other lifting surfaces to counter this moment. And that's it. This was a long one, so let's review. We started by identifying the 2 ways that a force on an object can be felt, pressure and shear. Simple examples of cylinder flow showed us how distributions of these stresses can lead to net forces on a body, both lift and drag. We defined the body forces that exist in a typical aerodynamic object, like an airfoil, and sought how to calculate the forces from the pressure and shear distributions. Along with the forces, we calculated the moment about the leading edge of the foil in the same way. And we found out how to calculate the center of pressure, the point where the body forces on the foil exist, but then quickly determined that it isn't terribly useful in practice. Thanks for watching, and I'll see you next time.